Hey, welcome back. This is the Human Exploration of the Moon and Asteroids session. I'm Jeff Plesha, and Kurt Klaus over there is the co-chair. We have a number of talks dealing with operating at asteroids and space and how things might work there. The first talk is by David Gump, Thermoelectric Propulsion, Solar Thermal Propulsion, Practical Technology for Solar System Exploration.
So at Deep Space, we're looking at solar thermal in the context of the 21st century solar system. Quite different from last centuries. There seems to be water everywhere, including near-Earth asteroids, which are conveniently not located at the bottom of a gravity well. And we're also looking at in terms of the new kinds of missions that are being contemplated. NASA headquarters slides for going to Mars actually have permanent space-based elements for their Mars mission architecture, which is a great evolution. And from our parochial perspective, harvesting space resources also is a round-trip activity. And the other thing great about the 21st century is there are a boatload more NEAs charted and available than last century. And a great deal of these, a very useful fraction, are closer than the moon. Some that we've identified require really only a few hundred meters per second of delta V to deliver their material back to Earth orbit, where they can support both commerce, ComSats, recon satellites, Bigelow habitats, and expeditions out to the moon and Mars. We got into solar thermal propulsion studies based on work we did for NASA for the asteroid redirect mission. We were comparing how NASA's going about the ARM with what an eventual commercial sustainable architecture for asteroid resources might look like, to try to trace the connections between those two and what the differences would be between those two. So we set a somewhat arbitrary task of getting 1,000 tons of volatiles into a high Earth elliptical orbit to serve the geocomsats, to do for the fuel for permanently space-based transfer stages and moon on Mars missions. That 1,000 tons is enough for one mission to Mars and a few years of consumption from the commercial sector. And the two approaches that we looked at were solar electric, what's being used for ARM, and solar thermal. For solar electric on a commercial basis, we need to return about 10,000 tons of regolith to get 1,000 tons of volatiles extracted, assuming a 10% conversion from the regolith. And for solar thermal, we would process that regolith at the asteroid and get 2,000 tons of volatiles, use half of it to get the remaining volatiles back to high Earth orbit. We can't do that on-site processing for solar electric because asteroids basically don't have xenon. There's no way to get that kind of fuel from asteroid resources. And when we looked at what it would take in terms of time and the fleet, there was a dramatic difference. In the solar electric case, we had to build a fleet of 8 vehicles, and it would take 20 years. Partly because it takes 5 to 6 years with solar electric to do the round trip, and partly because when you're bringing back raw regolith, you're only getting a net of 30 tons of water per trip. So that's 33 trips total. Whereas in the solar thermal case, it's just 2 vehicles on our fleet, and everything is done in 6 years because our round trips can be much shorter, and we bring back 250 tons of net water per trip for only 4 total trips. So this means that if you're looking at a long-term infrastructure, you really need to look at solar thermal as the answer to how do you do it at the lowest possible cost and make it sustainable. Another great thing about solar thermal is that it's scalable in terms of starting off at smaller scales and moving to higher scales. You don't have to do component level redesign. If you increase the power, you just increase the mass flow, but you stay at the same temperature. You're not fundamentally changing your system. Solar thermal has been studied before, but in a much different context. People were imagining launch from Earth, not using space-sourced propellants. And because they were launching for Earth, they took the best possible propellant, which would be hydrogen. But that also means that they had to use it immediately, more or less, keeping hydrogen cold so that you could use it when you arrive at Mars is a hard task. The image is from the Shooting Stars experiment that was intended to fly on the space shuttle. Now, traditionally, water from space sources has been turned into cryogens, liquid hydrogen and oxygen. We prefer to look at the simplest way to utilize space resources because we want to have the lowest infrastructure cost to get going. So, sunlight into a water tank that produces thrust is very simple compared to what you do if you have cryogens. There's a lot of conversion of sun into electricity where you're dumping 65% of your energy overboard and not using it, masked for the electrolysis, more electricity to do the liquefaction, and perhaps even most painfully, you have to add mass to your rocket, the last place you want to have mass, for the insulation or continuous refrigeration to keep it available for when you arrive at Mars, 5 or 6 months later. And from an engineering standpoint, I would rather not try to requalify a cryogenic thruster in space where your analytical base and test space is going to be very constrained. So in terms of Mars missions, one thing that we believe is very important for NASA to actually, or Elon, to get to Mars is that you can substitute the volatiles from space for the volatiles you launch from the ground. And in the latest design reference mission 5, 3/4 of the mass put into low Earth orbit is volatiles. If you switch to using space-sourced volatiles, you probably can get that 7 SLS launches down to 3 or 4 in that 26 months. Besides putting less strain on your manufacturing capability, it puts a lot less strain on your budget, which is probably the limiting factor in being able to get a Mars mission actually launched. And if you have somewhat more abundant mass available to you, you can do Mars in a more safe manner. DRM-5 now contemplates having a single Mars ascent vehicle to get the astronauts off the red planet and back to home. Having that single Mars ascent vehicle sitting on the Martian surface for more than a year and being absolutely positively certain that it's going to work would be, stomach clenching for me. I think it would be good to investigate space resources in part just to increase the safety of going to Mars and going back to the moon. We've plugged solar thermal into the models and found that you get a very useful payload traction to Mars orbit. Your transit time is a little bit shorter than the traditional chemical transportation time, so you're not giving anything up by switching to a solar thermal baseline. So we've begun work on this with the design of a nanosat for testing solar thermal, in part just to break the imagination barrier and actually do solar thermal in space. Since it's water as a propellant, it can be launched from the International Space Station and actually handled by astronauts without any safety concerns. Did I mention it's scalable? The principles that you can confirm in a small scale do in fact scale up to larger vehicles that you'll need to actually go off and do round trips to our targets. And finally, one of the other great things about solar thermal is that the collection mechanism for your propulsion can be used at the target to heat the regolith and extract the volatiles you need for your propulsion system. So it's an elegant way to have some of your mass do double duty. So that's a summary of why we are leaning towards solar thermal propulsion and what we're doing to try to get it kick-started. Thanks very much.
questions?
Derek Sears, NASA Ames. So the steam engine drove the Industrial Revolution. You think it might drive the commercialization of space?
Yes, because we're interested in simplicity. We don't have massive
That's a
budget.
cool thought. Okay. My question really was about your comment about xenon. You're presumably talking concentrations because meteorites are rich in xenon. There's really quite surprisingly high abundances, and it's really easy to extract. So what sort of concentrations were you thinking of when you said there's no xenon in asteroids?
Concentrations that could be harvested in a short enough stay at the asteroid to get you the tankfuls that you need.
You've looked at the numbers. You've really looked at the xenon concentrations in meteorites and worked it up.
Yeah, John Lewis is our chief scientist,
Oh, okay.
and
He knows about xenon in meteorites. Okay.
He's pretty confident. Yes, exactly.
Have you looked at mining argon, which is almost as easy to use as xenon in an ion engine? In Mars, the Martian atmosphere has almost 30%.
Well, we're going to asteroids, so
yeah. Well, you also were talking about going to asteroids to supply the fuels to come back from Mars and stuff, and the best fuel to take off from the surface of Mars is, and the easiest to produce is methane, LOX.
Mm-hmm. Absolutely. What we're proposing is that for your interplanet transportation, for your in-space transportation, water is a pretty good compromise. Solar electric with xenon argon is very efficient, very mass efficient, but it takes a long time to expend. To get a shorter time to expend and therefore realize the thrust, you have to go up to extremely high power levels, and that's hasn't been done yet. And we think that solar thermal probably is a good compromise in terms of efficiency versus speed. Right. We try not to ignore important things. Bruce?
So David, I may have missed it, but did you talk about the kind of performance you're expecting to get for either thrust levels or ISP from the thermal system?
We think that the ISP is going to be somewhere in the 190 range for normal temperatures of 300 to 400 C. Our experts have some uncertainty as to if you pump up that temperature much higher, do you in fact get a higher ISP? We've not been able to find any research in what happens when you really crank up the temperature. Does that energy result in a useful increase in the thrust? There's dispute. So that's one reason to do the nanosat, is to come up with credible results. And it's very hard to do that kind of thing in a vac chamber on the ground. People